So now that you've seen what a monitor is, we talked briefly about the monitor objects that are built into Java. We talked about the monitor object pattern briefly. I showed you synchronized methods, showed you synchronized statements. We talked about the coordination mechanisms, wait and notify all. Let's wrap up by talking about some of the usage considerations of Java's built-in monitor objects. So the most important thing to realize is that they come along with certain traps and pitfalls that you have to be very careful of. So there's a bunch of issues with monitor objects. They're very limited in a lot of ways. So they don't support non-blocked entrance. They don't have timed entrance into the entrance queue. And they don't support interruptible synchronizers in the entrance queue. So if you want that kind of finer grained control, use a Java reentrant lock, which is one reason why they're used very frequently within the Java class libraries, because they give you a lot better, finer grained control over the primitives. Synchronized statements only support scoped locking, so you only supports where you come in, acquire the lock, do something, and then release at the end of the block. And there are certain use cases where that just isn't the right thing to do. And one of the consequences of the scoped locking feature is that you may have to end up doing extra redundant checks. You can't optimize things in clever ways. And you'll actually get a chance to see that for the assignment 3B that'll come up soon. There's no sensible support for timed waits. They have this timed wait mechanism, but it's ridiculous, and you can't tell whether something timed out or not. It's just completely pointless. So that, again, is another reason to avoid the built-in monitor objects. And there's only one wait queue and one entrance queue. So they're just very limited in lots of different ways. The fact that you only have one wait queue and one entrance queue has a number of problems, not the least of which is something called nested monitor lockout. And you can read more about that here. In a nutshell, what happens is you come in to a method, the synchronized keyword acquires the intrinsic lock. And then inside of this, we're going to try to synchronize on a nested object, nested monitor, but we're still holding the outer lock, because when we call synchronized on this one, the outer one's not released. And so if someone comes along here and tries to call another method, it can't get in to access its intrinsic lock because it's locked here. You also can't support the two-lock optimization type of thing we talked about, which you'll find if you take a look at the linked blocking queue. If you take a look at linked blocking queue, which is this other implementation of a blocking queue that's part of Java class interface, you'll see that they do this clever optimization for locks that are taking things versus locks that are putting things. And they distinguish them so that things are faster. There's less contention. Choosing between notify and notify all is very tricky, not unlike choosing between signal and signal all was for condition objects. You can only use notify versus notify all if two conditions hold. First is uniform waiters. Everybody who's waiting on the implicit condition object is waiting for exactly the same thing to occur. And one in, one out, which means that you only want one thread to go ahead after it's been notified. The problem is, this is the problem, because of the fact that you have to use notify all over the place, having uniform waiters is very hard with condition objects unless you have very simple things you're waiting on. So you should try to use notify wherever possible to avoid the thundering herd problem, but this is easier said than done because of the fact that there's only one wait queue. So you may have to use that one wait queue to wait for all kinds of different condition expressions, as we saw before. There's also some tricky fairness issues that arise due to the order in which waiting threads are notified. It's really up to the operating system to decide how it wants to wake things up. You have no control over that. And that's what's typically called haphazard notification. Haphazard notification is great if order doesn't matter, because it optimizes the performance at the hardware level or the system level. But if you need to wake things up in a particular order, it is detrimental. So the thing to do is to use something called the specific notification pattern. We will talk a lot about that because that's programming assignment 3B is for you to use the specific notification pattern to guide your implementation of a fair semaphore, which has got better semantics than your simple semaphore does. So we'll talk about that. Specific notification basically lets the system choose, lets you, the user, decide which thread to go next, say in FIFO order. In practice, you typically need more than the Java built-in monitor objects. So of course, there's all kinds of good stuff in Java concurrent and Java concurrent locks, like reentrant lock, like condition object, and so on and so forth. And we've talked about those things before. And you can see plenty of examples either by looking back at the videos or by going and reading portions of the Java source code, which use these additional synchronizers heavily throughout the Java class libraries. Android also has lots of other stuff that go above and beyond what monitor objects have. They can use message passing. There's a thing called a message queue that avoids a lot of the needs for this stuff. And you really don't find synchronized used very much in production apps. It's usually used for very simple things.